All right, and as we do with all of our graphs, we do have to talk about transformations. Now, these transformations should look familiar to you because they're similar to the transformations we talked about previously. So recall our parent function is b to the x power. So here's our transformation standard form. We have a on the outside, which if it's negative means a reflection across the x-axis or a stretch or compression. We have our h here, which is our horizontal shift, positive left, negative right, and k on the outside is our vertical up and down. So let's take a look at number 1. Now the trick here is we have to first identify what the parent function was. And remember, the parent function is some constant to the x power. So by looking at problem number 1 here, my constant to the x power is going to be 3 to the x. That's my parent function. So what's the transformation? The only thing different is this plus 5 on the outside, which means it went up 5. But if I take a look at number 2, again, I need to identify the constant raised to the x power. And that here is 1/4 to the x power. Here I have a couple more changes though. I have that 2 on the outside, and that's bigger than 1, so that means it's a stretch. I have a vertical stretch by 2. And then I have this -1 up in my exponent. That's the h. That's a horizontal shift. And because it is negative, that means I'm going to the right 1. So those are the transformations for problem number 2 there. All right, now let's graph one. Let's take a look at number 5 here. Number 5 is really similar to the one that we graphed in our first video, because the parent function here, if you'll pay close attention to, my parent function is 2 to the x power. So what's our transformation here? I have that plus 5 here. That's going to be an h. And because it's positive, that means I am going to the left 5 here. Left 5. Okay. So let's figure out how we're going to graph this. If I recall back to my original function, parent function, we graphed that already. So we know what those initial points are. So this was for our parent function. Now for our transformed function, they're going to be the same, except that they're going to be shifted to the left 5 units. Now left, that's horizontal. That's our x value. So our y values are not going to change for this transformation. Our y values are going to stay the same. It's our x values that are going to shift to the left 5 units. So in the negative direction, 5 units. So I'm going to subtract 5 from each of my x values to get my new x values. So -2 minus 5 gives us -7. -6, -5, -4, and that should be 4, -3. So I'm going to graph those now really quick. 1, 2, 3, 4, 5, 6, 7. Okay. And it's not perfect by any means, but this is our new graph, more or less. Okay, and now notice again, our y is never going to quite touch 0, so this is where our asymptote is going to be. We can already see that. So it's the same graph, just shifted to the left 5 units. So our domain is still all real numbers, and our range y values can be anything that is positive, so y is greater than 0. So let's talk about end behavior again. As x is going positive infinity, so this is going to the right, what is happening to my y values? As we go to the right of our graph, y is increasing. So that's going to be going to positive infinity. Then as we go to the left, as x goes toward negative infinity, y is getting really, really close to 0. So let's talk about our y-intercept. Remember, y-intercept is when x is equal to 0. Now to identify exactly where that is, I can plug in 0 for x to my function. So 2 to the 0 plus 5 power is 2 to the 5th power, which is 32. So my y-intercept is 0, 32. And again, we know our asymptote is at y equals 0.